Hi class, so we are here to the end of the semester. This is the last section of the book we'll be doing this semester. This is integration by substitution. Now, integration by substitution is very important. It's very useful because it opens up a whole new class of functions for us to be able to antidifferentiate, and then later on in the lesson we will find the definite integrals of this new class of functions, and this new class of functions is composite functions. So recall how we went through the first couple lessons on derivatives without being able to take the derivative of a composite function. We took the derivative of things like x squared and sine of x, but then we couldn't, at least at first, take the derivative of things like sine of 3x or cosine of 6x or x plus 5 quantity raised to the 5th power. Now, if we wanted to do something like that, we could have expanded expanded the expression and then taken the derivative of a bunch of individual terms, but that would have been tedious. So let's just review what the chain rule did for us in differential calculus. So let's just review chain rule. Chain rule was for composite functions. And the chain rule essentially said this: if you want to take the derivative of a function that's a composition, so let's say like f evaluated at g of x. All right, we had the rule that said, and the chain rule that said, you take the derivative of your outside function. So here, f is the outside function and g is the inside function. So the chain rule said you take the derivative of your outside function, so f prime, you evaluate it at your inside function, which is g, but then you multiply by the derivative of your inside function. So that is what the chain rule told us. Let's just do a quick example. So let's say we have something like, we want to take the derivative of cosine, let's do sine of 4x plus 2. Okay. So sine is the outside function, 4x plus 2 is the inside function. And what the chain rule says is that this derivative is equal to the derivative of the outside function. The derivative of sine is cosine. But we evaluate, so it's cosine x is the derivative of the outside function. But we evaluate that derivative at the inside function, so 4x plus 2. But then we have to multiply by the derivative of the inside function, so the derivative of 4x plus 2. And so the final answer we get is cosine of 4x plus 2 times the derivative of 4x plus 2, which is just 4. Okay? So that's what the chain rule gave us. It gave us the ability to take the derivative of lots of different types of functions because lots of functions are composite. And so now we could deal with composite functions, take the derivative, do things like find slopes and find tangent lines and find maximas and extrema, find concavity, all that kind of stuff. And that's what the chain rule allows us to do. Now, here's what we have in, now that we're in chapter 5 with integration and antidifferentiation. We have the analogous rule. It's called U-substitution, so integration by U-substitution. Now that's Theorem 5.13 over here. So this is called U-substitution, and what U-substitution allows us to do, so we'll always abbreviate this U-substitution. What this allows us to do is reverse the process that the chain rule did. So the chain rule, let us take the derivative of a composite function. U-substitution is going to allow us to take the antiderivative of a composite function. So let's see what Theorem 5.13 says. It says, let G be a function whose range is an interval I. Let F be a function that is continuous on that same interval I. If G is differentiable on its domain, and F is an antiderivative, if capital F is an antiderivative of lowercase f on that same interval, then the antiderivative of f evaluated at g of x times the derivative of g of x dx is equal to the antiderivative of f evaluated at g of x plus c. So notice this is exactly what the chain rule gives us. F, okay, oh, you're about to tell me I'm wrong. F, I have f prime over here, evaluated at g of x, times the derivative of g of x. You tell me, well, there's just an f over there. But let's see what the conditions are here. The conditions are that lowercase f is the derivative of capital F of x. So that's why this looks a little different than our formulation in chapter 3 with the chain rule. So we can rewrite, let me rewrite the chain rule for us in that case. I'll rewrite it for chapter 5. The derivative of x, or excuse me, the derivative with respect to x of capital F evaluated at g of x is equal to lowercase f, because remember lowercase f is the derivative of capital F, so evaluated at g of x times the derivative, oh, I need another parenthesis here, times the derivative of g of x. So that's how we can rewrite the chain rule if we just allow capital F to be the antiderivative of lowercase f. So this is what the chain rule gives us. So all that Theorem 5.13 is telling us is that, hey, all we have to do is look for things in this form where we have a composite function, f evaluated at g, times the derivative of the inside function. If we have a integrand of that form, then we know what the antiderivative is. We can easily find it, okay, because we know that the chain rule has to occur to get something that looks like this. Maybe it doesn't have to, but it usually occurs to get something in this form. So what we're doing is looking for integrands of this form. If we can find an integrand of this form, now in chapter 5 we are dealing with a differential, so we have to consider that there is a dx over here because we always have a variable of integration. So we're looking for integrands of the form a function evaluated at another function times the derivative of the inside function. And if that's the case, then all we have to do is take the antiderivative of f evaluated at g, and if we're in indefinite integration, add a c. Now, the g's and x's and stuff, and the g's, f, and x's, sometimes we get tired of saying f evaluated at g and all that stuff. So usually what we do is we say just let u be a function. Let u be the inside function. And so what we will call this is f of u du form. So what we're looking for is f of u du form. And that's where the U-substitution name comes from. So instead of having f's, g's, and g primes, what we'll talk about is having f as a function of u, and then the derivative of that function is du. So this is what we're looking for, f of u times du form. So if we can find functions, integrands, that are of this form, we can easily integrate them by just reversing the chain rule. So I will give you a fair warning. These come with practice. Students find to Students typically find that these are pretty difficult to start with, but once you develop an intuition from practicing these a lot, they're not bad at all, but you have to practice. Like I said, you develop an intuition to where all of a sudden you can see a lot of the steps in your head and do a lot of simple pattern recognition in your head. Now, some of the more difficult ones, you're always going to need to write all the steps. And I'll write out all the steps to start with. After you practice this a while, you will get a nice intuition for doing U-substitution, some of the steps mentally. Okay, so let's see here. Let's see. We're not going to do change of variables just yet. Let's do some of the easier ones. Okay, now the harder ones are when we change variables and do more of the steps on paper. But let's do some of the easier ones to start with. So we're just going to look at antiderivatives for the time being. We haven't talked yet about definite integrals. We'll get to that, Theorem 5.15 here in a little while. But for the time being, let's just look at some antiderivatives. So let's start off easy. Let's look at the antiderivative of x times x squared plus 1 squared dx. Okay, so currently, if we were prior to section 5, chapter 5, section 5, the only way we would know how to take care of an antiderivative such as this would be to expand this binomial, multiply by x, and then take the antiderivative of those resulting 4 individual terms. Is it hard necessarily? No, but it's tedious. Especially, let's imagine that's not a squared. Let's imagine that's to a 4th power. Well, if that's raised to a 4th power, then that expansion and then distributive property ends up being quite cumbersome. But if that's a 4th power and we use U-substitution, then really it's no big deal at all. Now here's how U-substitution works. Let's identify the inside function. Okay? The inside function is x squared plus 1. Now this doesn't always work, but usually what we want to look for is the inside function, and for the easier ones that will usually always be the case. And so the inside function is x squared plus 1, and notice that we almost have the derivative of the inside function elsewhere. We almost have the derivative of the inside function outside here multiplied. Because what's the derivative of the inside function? Let's just write this out. Let's just say u equals x squared plus 1. What's the differential of u? Well, du equals, the derivative of x squared is 2x. The derivative of 1 is 0, but we're taking a differential here, so it's dx. So notice we almost have du. So we almost have the derivative of the inside function. The derivative of the inside function is 2x dx. We have an x and a dx. Now, if it makes you feel better, we can write this as x squared plus 1 squared, and just rearrange here. That's x dx. These are just 3 things multiplied together. We can rearrange them however we want to. So we have an x dx, but we need a 2x dx to be in the exact correct form. Remember, we want a composite function, so f evaluated at an inside function times the derivative of that inside function. Well, we almost have that entire derivative, but it is we're missing a 2. Now, how might we get a 2 right here? Because if we have a 2 there, then we have a function, an inside function raised to the 2nd power times the derivative of that inside function, the differential of that inside function. Okay, but I can't just add a 2 there. Okay, but we do have a rule of antiderivatives and for definite integrals as well. that we can do this. We can factor in or out constants. Okay? So if I have, let's say, a 2 there, I could factor a 2 in and put it right there instead. But I can't just multiply this antiderivative by 2. That would change the solution. But what I can do is multiply by a specialized version of 1. 2 over 2 is a special version of 1. But then what can you do? You could break that apart into, say, 1/2 times 2. Correct? We didn't change anything. And then we have x squared plus 1 squared x dx. And now what can I do with that? Just the 2. I can take the 2 that I need and put it right here and leave the 1/2 out front. They're both constants. We can take constants in and out of the antiderivative. And so we have now x squared plus 1 squared times 2x dx. And now what do we notice? We notice that we have a function. We'll call this function, we'll call it g. We have g raised to the second power times the derivative of g. And we know that, how could we reverse that process? Well, we could say if you really want to make this complete substitution, we could make this substitution and say this is 1/2 times, x squared plus 1, we call that u. So it's u squared. Now what's 2x dx? That's du. And now how do we antidifferentiate u squared? Well, that's easy. Just imagine, u is just a variable here. Imagine it's an x squared dx. What do? Well, we increase the power. We increase the power by 1, and we divide by that new power. So it's u cubed over 3, which of course equals u cubed over 6. But we don't want to have the u in our final solution. We want to have x's in our final solution. So what is the if we back substitute to get our final solution? U is x squared plus 1, so we have x squared plus 1 cubed over 6. Oh, you know what I forgot to do here? I always forget that. We need a plus c there. We need a plus c there. And we need a plus c there. I get so used to doing definite integration that I always forget those plus c's. Okay? Now, notice if we had recognized completely the pattern, we could have realized, we have a function times its derivative. To reverse the process, just take your outside function, and in this case, it's a power function, so increase the power by 1, divide by that new power, and then we have a 1/2 out front. And then we would get the exact same answer, but it's a lot of students find it's less ambiguous if you do convert to the u notation. Just remember to convert back to the x notation if you're doing just plain antiderivatives. Now we'll see the situation's a little different once we get to definite integrals. We can change over to u's and then stay with u's. You don't have to change back to x's. But with the just regular antiderivatives, we will need to convert our final answers back to the original variable, which is usually an x. Now, truth be told, I meant to do a slight easier one, but I looked at my notes and picked the harder one first. Let's look at an easier one real fast. Let's look at the antiderivative of 5e to the x dx. I meant to start off easy, but I looked at the wrong portion of my notes. So this is a little bit easier one. Okay? So, oh, I missed a little part. E to the 5x dx. Otherwise, this is not a composite function. 5x dx. Okay? Now, what we're looking for is a composite function times the derivative of the inside function. And what do we notice here? We actually notice here that we have just that. I mean, it's not organized maybe properly, but we do have what we need. Let's change the order here. And notice we have e to the 5x times 5 dx. Again, just don't let these things throw you off. Dx is just an item. 5e to the 5x is just an item, and 5 is just an item. We can use the commutative property of multiplication to rearrange those three things however we see fit. So notice I just transposed e to the 5x and 5. But notice what we have here. We have a function, composite function, e raised to the 5x, and then we have the derivative of the inside function 5 dx. Again, when I say derivative, I do mean differential here. If I take the differential of 5x, so the derivative of 5x is 5 times dx, the differential. Now, if you want to make like the formal substitution, let u equal the inside function 5x. So what's the differential of u with respect to x? The derivative of u with respect to x is 5 dx. Imagine, this is what we're doing here. We're taking the derivative of u with respect to x. So we're taking the derivative of both sides of this equation with respect to x. So you get a 5 over there. But du, if we just want du, then we can say du equals 5 dx, and we can get rid of that. So this was like that section 4.8. If you've forgotten about differentials, just look into section 4.8. We covered differentials in that section. Okay, so du equals 5 dx. So if you want to, then we can just you can make the formal substitution, and you could say this is the antiderivative of e to the u times 5x, which we know is du. And now how do we antidifferentiate e raised to a power? Just imagine that u is just a variable, and it's the same variable as integration. So we know the antiderivative of e to the u is just e to the u plus c. Always remember, your variable of integration always disappears once you take the antiderivative. Okay, so now we don't want to leave our answer like that because we want our final antiderivative solution to have x's in it if we're just finding a regular old antiderivative. So we know u equals 5x, so then we just make that substitution. E to the 5x plus c. So I hope you can see how this technique is super useful, because now we can look at all kinds of new functions where we have composition happening. And again, sometimes we could probably find the answer another way, occasionally, but that other way would probably be more tedious. Now, this might seem tedious to you at the moment, but once you have a lot of practice, then I promise this won't be a big deal. Okay? And in a lot of the cases, U-substitution will be your best bet for sure to figure out the antiderivative. Okay. Now let me address a few common mistakes. There's a few common mistakes I see a lot, and here's probably one of the biggest ones. We'll be trying to find, say, actually, let's just go to this example we just looked at. Let's say we have this example here. I'll just write it up here. I'll write it in pink, so make sure we'll cross it out and say we can't do this. A common mistake is to say the first step here to find the antiderivative is the antiderivative of x dx times the antiderivative of x squared plus 1 squared dx. Okay, a common intro to anti-differentiation mistake is to say, well, I can just take the antiderivative of the first one and the antiderivative of the second thing and multiply the answers. But that's not the case. So don't make that mistake. Okay, we don't have a method, or excuse me, we have U-substitution, but we cannot simply take the antiderivative of the product of two functions. We can't take the antiderivative individually and multiply those answers. Just like we couldn't do that with derivatives. Recall that if we had the derivative of a product, so f of x times g of x, we couldn't simply take the derivative of f and the derivative of g and multiply the solutions. We had to use the product rule. The exact same thing was true for quotients. Recall, if we had f of x divided by g of x, we couldn't simply take the derivative of the numerator, the derivative of the denominator, and then just look at the quotient of those two derivatives. We had to use the quotient rule. So just like those two things were true, we can't take the antiderivative of the first item, the first part of the product, and the second half of the product, and multiply the two answers. In this case, we would either have to expand, that is, multiply all these terms together, and then break the antiderivative, the integrand, apart into four antiderivatives, or we have to use U-substitution. Okay, U-substitution will be faster in this case. Okay, so don't avoid that common mistake. I see that a lot. I just wanted to bring that up because we see that pretty often at this point in the semester when we start looking at these more unique integrands. Okay, remember the integrand is all of the stuff to the right here. I shouldn't say everything to the right, because the dx that is the variable of integration. So the integrand, when I say integrand, this is what I mean. All of this stuff right here. So whenever you see a product, an integrand that is a product, we're probably going to need to use U-substitution, at least in this course. You'll have different methods to do this type of thing once you get to Calc 2, but for the time being, we're U-substitution or some other type of rearrangement, if possible, will be required. Now, let's look at another easy one. Then we will go off to some more difficult ones. Let's say we have the antiderivative of x squared plus 5 raised to the 6th power times 2x dx. Now I say this one is easy because if you look to see what's going on, look at your inside function and think, what's the derivative of that inside function? Well, sorry, I keep saying derivative. What's the differential of that inside function? The differential of that inside function is 2x dx. So this actually fits the pattern perfectly to reverse the chain rule, to use U-substitution. Now, you don't have to do a formal conversion to use here, but it doesn't hurt to write out all your steps. So we could say, okay, look, there is a function x squared plus 5, and there's its differential. So we have the exact form f of u, some function of u, times du. That's exactly the form we have here. So this fits the bill exactly. Now, if we want, we could say that u equals x squared plus 5. If u equals x squared plus 5, then what's the differential du is 2x dx. So if you want to make the formal substitution, we could say this is equivalent to the antiderivative of u to the 6th power times du. Just by substitution. X squared plus 5 is u, so u to the 6th power. These three terms here, these three items multiply together, and that is exactly what du is. And now we have this really simple antiderivative to take care of. It's just a power rule antiderivative, and we know that's u to the 7th over 7 plus c. So of course we're going to have to make sure we have that antiderivative list memorized, because U-substitution depends on having the power rule memorized, your trig antiderivative is memorized, your exponentials, that kind of stuff. So you have to have that list memorized, but if you have that list memorized, it's not so bad. And then of course the last step is that we just want to write our final solution in terms of x's. So we have x squared plus 5 to the 7th power over 7 plus c. And now, how would you check yourself? I've said this before. You never need to wonder whether or not your solution is correct, because all you have to do is take the derivative and see if you get the original integrand back. So let's just do that real fast. Let's look at the derivative of our solution. So the derivative of, let's see, x squared plus 5 raised to the 7th power over 7 plus c equals, okay, the chain rule, this would be a chain rule derivative, says, okay, we have this inside function raised to the 7th power, so we use the power rule for derivatives to start with, which says bring the original exponent out front, and then we evaluate x squared plus 5, reduce your exponent by 1, but there was a 7 there already, and then we multiply by the derivative of the inside function, which is 2x, and the derivative of c, of course, is 0. Now notice we have a 7 and a 7, so those divide out, and we have x squared plus 5 to the 6th power times 2x, and then that is our original integrand, x squared plus 5 to the 6th power times 2x. Okay, and if we were talking about a differential, we would have a dx there, which ends up being our variable of integration. Okay, so you can always check yourself with antidifferentiation. If you have an antidifferentiation problem, just differentiate, and then you'll know exactly whether your solution was right or wrong. If you get the original integrand back, then you're exactly correct. If you don't get the original integrand back, you made a little error somewhere. Okay. Now let's get progressively harder. Again, I kind of started off with a little bit harder ones. Let's go back to where I started off. This isn't too terribly hard, but let's look at the antiderivative of, let's say, antiderivative of cosine, let's just say 3x dx. So notice I haven't, in all of these, I'm just taking regular antiderivatives so far, nothing too crazy. Now, notice, if I just had the antiderivative of cosine, that's super easy. The antiderivative of cosine is just what? Well, it's sine. Okay? The antiderivative, and that's just in the list of stuff we've memorized, the antiderivative of cosine is sine. But here, I have the antiderivative, I'm trying to find the antiderivative of cosine 3x, not just cosine x. So this is composite. Now all we have to really recognize is that I need a function times the derivative of its inside function. Now notice, what is the derivative of the inside function? It's just 3 or the differential is going to be 3 dx. Okay, so if I want I need to find I want it in the form of cosine 3x times the differential of 3x, which is 3 dx. Well, notice I have a dx over here. All I need is a 3. So again, we have that constant multiple rule for integrals that says, well, you can factor in a constant or factor out a constant, whichever you need to do. So if you multiply by a 1, 3 over 3, but then separate that and say it's 1/3 times 3 is the exact same thing. But then what can you do? You can factor in that 3 that we need and leave the 1/3 out. So we'll have cosine 3x times 3 dx. So notice we have a function evaluated at another function. So let's say 3x is u. So we have cosine of u times the derivative of u. And so all we have to do now is reverse that process, and we know, now we have a 1/3 out front, we can't forget about that, but we have 1/3, and what's the antiderivative of cosine 3x? Well, it's sine 3x. Now, why did I do that without actually changing over to u's? Because I know if this is u, then this is du. So I'm seeing in my head, all right, I have cosine of u du. What is the antiderivative of cosine u? It's just sine of u. But what's u? It's 3x. So this is what I'm talking about as far as being able to just do the simple pattern recognition. So, of course, I always forget my plus c. So the final solution is just sine 3x over 3 plus c. If you're unsure of your solution, simply take the derivative. What's the derivative of c? Of course, that's 0. What's the derivative of sine 3x over 3? Well, the derivative of sine is cosine. Evaluate our inside function, so cosine of 3x times the derivative of the inside function. The derivative of the inside function is 3, so you'll have a 3 over 3, and you'll result with just cosine 3x. Here, I'll write that out just to make sure you got that. So the derivative of sine 3x over 3 plus c equals, okay, it's cosine, so the derivative of the outside function, evaluate it at the inside function, times the derivative of the inside function, that's all over 3 still, plus the derivative of a constant is 0, but notice 3 and 3, so we're just left with cosine 3x, which is exactly our original integrand. Okay, so I hope you're seeing kind of the pattern of how this is working out. We're just looking for f of u times du form. This is the key here. A function evaluated at u times the derivative of that function. That's exactly the pattern that the chain rule gave us. And so we're trying to reverse that situation. And so this is what we're looking for, f of u du form. A lot of times we'll call it u du form for short, but f of u du form. Okay, let's look at another trig example. So let's see here. Let's make it a little bit harder. Let's look at the antiderivative, maybe not actually hard, it's going to look harder. Antiderivative of 5 secant squared x times tangent of x minus 3 dx. Now, you might think this looks crazy, all this, secant squareds and tangents and negative signs and multiplied by 5 and stuff, but just really look at your inside function. And, inside function here, well, I guess it's kind of debatable what's inside, what's not. I guess this is more of a product than an inside function. But let's just look inside the parentheses here. And so let's let u equal tangent of x minus 3. Well, if that is u, then what do you think du might be? The differential du, what's the derivative of tangent x? That's secant squared x. What's the derivative of negative 3? It's 0, so it's dx. So what do you notice here? We have u here inside the parentheses. We have secant squared over here. We have a dx over here. All we need here, so here's a kind of a funny situation. All we need to get in u du form is a secant squared on the outside and a dx. But I have this 5 over here. But what can we do with that 5? Well, it's a constant. You can factor it out. We don't need it to get our u du form. Usually, what we're doing, we need to factor in, but here we need to factor out. So we take that 5 out, and notice that now we have, okay, let's just rearrange a little bit. This isn't strictly necessary, but I like the way it looks. Tangent x minus 3 times secant squared x dx. Notice, if this is u, then this is du exactly. So we have, we could, if you want to make the exact formal substitutions, you could say this is u du. And how do you antidifferentiate just a single variable? Well, again, that's just a simple issue, straightforward calculation. It is u squared over 2 and plus c, of course. Now, technically, recall our conversation from a few lessons ago. Technically, the 5 is multiplied by everything, but we don't have to distribute the 5 to the c. Because 5c, it's just a constant. So we'll just say this is 5 u squared over 2, and we don't have to distribute the 5 to the c, because 5 times a constant is still a constant, and so that's just plus c. Now, of course, we need to make our final solution have x's in it, not u's. And so what was u equal to? It was tangent x minus 3 plus c. That was a squared right there. Almost forgot. Okay? So we have to be adept at factoring constants in and out. Now, I will say here's another common pitfall, or maybe not super common, but occasionally it happens that you want to avoid. Avoid this pitfall. If you have so like the antiderivative of, let's just say, of the one we just did. So the antiderivative of 5 secant squared x times tangent. Oh, actually, let's change it up a little bit. Let's say 5x times secant squared x dx. Now, we know that the derivative of tangent is secant squared. So if it wasn't for this pesky 5 and this pesky x, I could just say the antiderivative was equal to tangent x. And so here's a common mistake I see occasionally, is that students say, well, just factor out a 5, which is fine, but also factor out an x, and say it's 5x times the antiderivative of secant squared x dx, and then say, all right, well, the antiderivative is tangent x, and then call it a day. But we can't factor out variables. We only can factor out constants. So be careful with that. You can factor in and factor out constants all day long, but you cannot factor in or out a variable. Okay, so just be aware of that. Variables have to stay in the integrand. They can't come out. They have to stay where they are. So just be aware of that. I just wanted to bring that up as a common, not an everyday occurrence, but somebody will just not have a temporary brain fart, and we take that out, and you can't take out anything that's not a constant. So variables have to stay where they are. So just be aware of that. All right, now we've done several easy examples. Let's do some of the harder examples where there's a couple more steps involved. Okay, the way our book terms this is that all of these examples could have been solved by what is called pattern recognition. That is, we recognize right from the beginning that this is almost in u du form, and all we need really is a 3 here, and then we can integrate pretty easily, antidifferentiate. Or notice here that this is automatically in u du form, and so then we just have to antidifferentiate. And technically, you could have done some of these steps in your head. That's what our book terms pattern recognition. But what our book terms change of variables is when you really need to write down all the steps, pretty much like we've been doing here, except these are going to be more complicated, where you probably, you could have gotten away with not writing all these steps here and done some of these steps in your head. Okay, but pretty soon here they're going to get complicated, where you really probably need to be writing all the steps down, making a formal substitution, and such. Okay, let's look at a couple examples. Let's see here. Let's scroll down. Let's look at some radicals. So let's see what happens when we look at the antiderivative of the square root of 2x minus 1 dx. Now again, the general rule of thumb is that you can let the inside function be u. I want to warn that that's just generally true. It's not always the case. But generally speaking, that'll be true. So let's see, what happens if we let u equal 2x minus 1? Now, once you make your substitution, go ahead and compute the differential, du. Du equals what? Well, it equals 2 dx. Okay, the derivative of 2x is 2, the derivative of negative 1 is 0, and we multiply by dx, the differential. So we have the differential over here. And now let's see about the making substitutions. Okay, we could say this is equal to the antiderivative of, okay, it's the square root of u, but I still have a dx. Now here's the thing. Here's, I guess, another common mistake. We can't have dx's or x's and u's mixed together. We either have to have all x's, like we do when we're starting here, or we have to have all u's. We can't have du's and x's, or u's and dx's. It has to be u's and du's, or x's and dx's. So I need to make a substitution over here. And what do we notice? Well, I know that dx, I almost have dx over here. One way to think about it is that this, du over 2, dividing both sides by 2, equals dx. So now I can make a proper substitution and say this is the antiderivative of the square root of u times du over 2. Now notice I don't have exactly the form I want. I just want u du, But what can I do with this 2 on the denominator? Notice I have this item multiplied by this item, which the 2 then divides it all. So it's essentially like multiplying by 1/2. I can pull out a 1/2 and say this is the antiderivative of the square root of u du. And now how do we anti-differentiate radicals? If you recall from section 5.1, maybe section 5.4, we always change to exponential notation. So let's just erase that square root. And what is the power that represents a square root? Well, it's 1/2. And now that's pretty easy to take care of. So we have a 1/2. What's the antiderivative of u to the 1/2? Well, we increase the power by 1 and divide by that new power. So it's u to the 1/2 plus 1, which is 3/2, divide by that new power, which is 3/2. We have to add that plus c, of course. Technically, we should probably put parentheses like that. And then we need to simplify. Let's see. We'll have a 1/2. We flip the 3/2 in order to multiply and simplify. So 1/2 times 2/3 is 1/3 times u to the 3/2. We don't have to worry about distributing the 1/2 across the c, so we can just say plus c. And there we go. Oh, we need to make our last substitution back to x's. So it's 1/3. Now what did u equal? 2x minus 1. That was raised to the 3/2 power plus c. So there you go. You want to check yourself? Go right ahead. Take the derivative of your answer. The derivative of the antiderivative should give the original integrand. So let's see, if I use this will be a chain rule derivative. So the chain rule says take your original exponent, write it out front, and multiply. So we'll have 3/2 times 1/3. That gives us 1/2. All right, actually, let's just go ahead and do this. I'm going to show you how this is really cool. So the derivative of 1/3 times 2x minus 1 to the 3/2 power, we get, okay, you take the original exponent and write it out front and multiply. So we have 3/2 times 1/3 times the original inside function, but now we raise it to the 3/2 minus 1 power, that's 1/2. But then what's the last thing to do? The chain rule says you have to multiply by the derivative of the inside, which is 2. So we have 3/2 times 2. That results, 3/2 times 1/3. That results in 1/2. 1/2 times 2 is just 1, and so we're left with just 2x minus 1 to the 1/2 power, otherwise known as 2x minus 1, the square root of 2x minus 1. So this works out nicely. Okay, so as long as you understand very well how the chain rule works, U-substitution shouldn't be that big of a deal, especially for the more easy ones. Now, they are going to get harder here in a few minutes, but for these easy ones, you always check yourself, and just always remember, we're trying to reverse the chain rule. Okay, let's do an example almost just like this, but a little bit different. A little bit different. Let's look at the antiderivative of x times the square root of 2x minus 1 dx. Now here's where you want to avoid those two common pitfalls I've already mentioned. You don't want to try to take the derivative, you don't want to try to take the antiderivative of x and the antiderivative of 2x minus 1 individually and then multiply the results. We have to use a formal U-substitution here. We won't be able to do this in our head because this one looks to be like it's going to take a little more work. And let's just see what happens. If let's just assume that The inside function is going to be our u. So let's let u equal 2x minus 1. What would the differential be? Well, this is exactly the same substitution we made in the last example. So du equals 2 dx. And let's see where that gets us. Okay, so we are going to have the antiderivative of x times the square root of u times dx. Okay, now we can do the exact same thing we did earlier and say, okay, well, dx equals du over 2. And we can make that substitution. So let's just go ahead and erase here, save as a line. So we say du, oh, not ud, du over 2, okay. And again, just like the last example, let's factor out that 1/2 and say this. So we're exactly to essentially this step, but the problem is we have an x still, okay, and we can't have x's and u's mixed together. Okay, we have to have all u's. We're changing over to u. We have a du. We have a square root of u. What can we do with that x? Well, go back to your original substitution and solve that for x in terms of u. So what can we do here? We could say that u plus 1 equals 2x, or u plus 1 over 2 equals x, just by working with that original substitution. And now we can replace and say we have 1/2 times the integral antiderivative of u plus 1 over 2 times, let's say, u to the 1/2 power du. Now you might say to yourself, that doesn't look any better at all, but I think we can use some basic rules of exponents to make this look a lot better. Let's see here. We have 1/2 out front. Can't lose that. Now, we can break this apart into two fractions. We could say that is like u over 2 plus 1/2 times u to the 1/2 du still. So 1/2 times the antiderivative. Now, let's think about this. We have u over 2 times u to the 1/2. So we're going to multiply distributing here. What's u to the first power, which understood 1 there, times u to the 1/2. The rules of exponents say you add the exponents in that case, and we have u to the 3/2 over 2 in that case. What's 1/2 times u to the 1/2? Well, it's just u to the 1/2 over 2. Now we do have this du, the variable of integration. And now what do we have? We have two terms that we can take the antiderivative of. Now technically we're taking the antiderivative individually, but we don't have to break this apart. We can just take it, the antiderivative, since we have the sum of two items, two terms. We can take the antiderivative of both of those individually. And so what do? We increase the power of each exponent and divide by that new exponent. So let's see. We have a, let's separate this. We have a 1/2. Okay, we have u to the 3/2, so that would be plus 1 would be to the 5/2 power. U to the 5/2 power divided by that new exponent plus, okay, u to the 1/2 power. I'm going to write that 1/2 out front like so. U to the 1/2 power, raise it by 1, that's the 3/2 power. And then divide by that new exponent plus c, and there we go. So just a little bit of cleaning up to do. We have a 1/2 out front. Oh, let's see. You know what I should have done earlier? I should have factored out that 2. I should have factored out had a 1/4 out front, but we'll get the same answer either way. Let's see here. So I have 1/2. Now I need to multiply by the reciprocal of 5/2. So that's 1/5. Okay, because I'll have 2 over 5 times 1/2. That's 1/5 times u to the 5 over 2 plus, all right, I have 3 halves. I need to take the reciprocal and multiply, so that's 2/3 times 1/2. That results in 1/3 u to the 3 halves plus c. Let's see here. We need to distribute, and then we need to make our final back substitution. So we have, let's see, u to the 5 halves divided by, okay, it's 1/5 and 1/2, so that's divided by 10. 1/2 and 1/3 is over 6 for the second term. So u to the 3 halves, then plus c. Now, lastly, we just need to make that last substitution. What we want our final solution to be in x's. So u equals 2x minus 1. So we have 2x minus 1 to the 5 halves power over 10 plus 2x minus 1 to the 3 halves power over 6 plus c. And there we go. Okay, so there is our antiderivative. So that's getting kind of tough, but there's none of the individual steps are too terribly difficult, but there's a lot of steps there. Okay, there's a lot of algebraic manipulation. You have rules of exponents. Your antiderivatives are not very hard, but you do have to remember, that you're dividing by this fraction. How do you divide by fractions? Well, you have to find the reciprocal and multiply. So there's a lot of moving parts here. Like I said, none of them are terribly difficult, but there are a lot of little places where you could go wrong. So just really take your time on these and go slow. Okay, so again, the general rule of thumb is just to let the inside function be u and see where that takes you. Doesn't always work. We'll see an example here pretty soon where it doesn't always work, but it's usually a good starting point at least. Let's see. Let's look at another trig one. Let's say we have. Let's see here. The antiderivative of sine squared of 3x times cosine 3x dx. So let's see here. That looks complicated, but I think if we rewrite it, understanding what sine squared written like this actually means, I think it won't be so bad. So remember, we kind of write trig powers weird. Like sine squared actually means sine 3x squared. That's what that literally means. We try to write like that just to be clear of where the exponent belongs. That's why we write it like that. But that's what this means. So times cosine 3x dx. Now what we notice here, now we clearly have an inside function. It would have been kind of hard to tell earlier what the inside function is, but clearly u equals sine 3x. So what do you suppose the differential du is? Well, it's the derivative of sine 3x. Okay, this is actually a mini chain rule. It's cosine 3x times the derivative of the inside function, which is 3. So we would generally write that as 3 cosine 3x. Oh, we missed the dx. Sorry, dx, we're doing the differential, so dx. Now, what do you notice? You notice you almost have what we need for du. Almost have it. Okay. So what we can do here is, again, we can multiply by a specialized version of 1, namely 3 over 3, and we can pull in the 3 that we need. So we have, let's see, sine 3x squared, and now we have 3 cosine 3x dx, and what do you know? What do you know? We have exactly the form we need. 1/3. If u equals sine 3x, we have u squared. This is du. 3 cosine 3x dx is du. And now we've simplified this pretty crazy looking function into just a simple power function, u squared. It's a quadratic in terms of u. So we have 1/3. What's the antiderivative of u squared? It's u cubed over 3 plus c. And of course, that simply gives us u cubed over 9. We don't have to distribute the 1/3 to the c. Last little step is simply to back substitute for x's. And so if u is sine 3x, then we have sine 3x cubed over 9 plus c. If you want to take the derivative to check yourself, simply take the derivative using the chain rule. So let's see here. We could say that the derivative with respect to x of sine 3x, let's see here, let's do this, sine 3x cubed over 9 plus c equals, okay, this is a chain rule application, naturally, since we're trying to reverse the chain rule, so if we're trying to see what happened originally, we're just using the chain rule. So let's see, the chain rule says bring the original exponent out front, so we have 3 times sine 3x, reduce the exponent by 1, so it's squared, now we do have a 9 still in the bottom, times the derivative of the inside function, which is cosine 3x times 3, that's the derivative of sine 3x, plus the derivative of c, which is 0. So let's see, 3 times 3 is 9, 9 divided by 9 is 1, so we're left with sine 3x squared times cosine 3x, which notice, cosine 3x, I could write a 3, that'd be nice, is our original function. Sine squared 3x, that is sine squared 3x, times cosine, if we do the differential, of course, that is dx. Cool, so again, the chain rule can be used to always check yourself. So you're taking a test, you're doing your homework, you should always know, even before you write your answer down in the software or on the test, you should know whether you got that question right or wrong, because you can always check yourself using the chain rule. Let's see here. We're about to go to definite integration, but before I do, maybe one more indefinite, and then we'll do some definite integration problems. So we haven't done anything with e in the past couple questions, so let's look at an e exponential example. So let's see here. I think this one looks interesting. We have the antiderivative of e to the x plus 1 times e to the x plus x dx. Now, with this one, it's what is an inside function, what's not. I mean, I suppose if you really wanted to, you could FOIL this and find you would have a couple of different terms, so I guess 4 different terms, and then you could anti-differentiate each of those terms individually. But I think the U-substitution might work well for us. And what you have to notice here is if you let one of these equal u, is the other one du by any chance? That is, if you let u equal e to the x plus 1, is the other one du? For instance, let's just say I make this tentative substitution. Let u equal e to the x plus 1. Well, in that case, what would du equal? Well, du would equal e to the x dx, the differential. Well, do I see e to the x dx over here? Well, I do, but it's e to the x plus x dx, so not exactly. So that doesn't work out for us. But what about if I let u equal e to the x plus x, the other possibility? Well, what would du be in that case? It would be e to the x plus 1. It's the differential, of course, so what do you know? Dx. So now we have u equals this factor, and du equals the other stuff. And so here we have a perfect substitution, and we could say this is equal to e to the x plus 1. I'm just strictly going to rearrange here, times e to the x, so e to the x plus x times e to the x plus 1 dx. Clearly, this is u, and this is du. So we have, let's see here, just to make the formal substitution, we have u du. And now that is a much more simple proposition, a much more simple antiderivative. What's the solution? Well, that's super easy. It's a u to the first power. How do you find the antiderivative of a variable to the first power? Well, it's u squared over 2 plus c. Last little step is just to back substitute. U is e to the x plus x. So that's squared over 2 plus c. And I think you'll see if you take the chain rule and take the derivative of this solution, you will get the original integrand back all over again. Okay, so that is indefinite integration with U-substitution. Now, what we want to do now is translate this into definite integration. The thing is, it's nothing too much more difficult. We're just going to have limits of integration and then have the fundamental theorem of calculus to apply. So just like in prior sections, we could find the antiderivatives, and then we could also use the fundamental theorem of calculus to evaluate a definite integral. Recall, if the function is non-negative over the interval of integration, then the definite integral will result in an area. If the function is not non-negative, then the definite integral will result in net area. So we can now use integration by substitution, U-substitution, to figure out the definite integrals, to evaluate the definite integrals of composition style integrands. So this is going to open us up a lot of new doors for us as far as finding definite integrals are concerned. So the only thing we have to be careful of is our limits of integration. That's really the only thing we have to be careful of. Okay, so let's look at an example. So notice these are going to look very similar, but they're going to have limits of integration. So whenever you have limits of integration, recall, we are dealing with definite integration as opposed to indefinite integration. So let's see. Let's look at the definite integral from 1 to 5 of x over the square root of 2x minus 1 dx. So notice, be on the lookout for the limits of integration. Since we have limits of integration, This is going to be a fundamental theorem of calculus problem where the result is not going to be a family of functions like it's been prior. Remember, prior we have the solution is a function plus a constant, so the interpretation is it's a family of functions is the solution. Well, now, when we have a definite integral, the result is going to be a number. And like I said, if the function's non-negative, that number will represent area under the curve between x equals 1, x equals 5, and the horizontal axis. If this function is not non-negative, then the interpretation will be net area. So let's see what happens. So let's see here. We want to use substitution. Again, this is a composition. It's kind of a complicated composition, it looks like. But let's just go with our general rule of thumb, which says let u equal the inside function. So 2x minus 1. Okay? So 2x minus 1. Now let's see what happens. If we so we have to be careful here because when we change over to u's, we can't use the same limits of integration. So this is another common pitfall, is that we switch over to u's and we keep the original limits of integration. But as soon as we change to u's, we have to change the limits of integration, and I'll show you how. So let's see here. If we make this substitution u equals 2x minus 1, well, first of all, we should say, what does du equal? Du equals, let's see, that is 2 dx. Okay, that's good so far. So, but what does dx equal? We could say that du over 2 equals dx. Okay, that's fine. So let's make a couple substitutions and see what we have so far. So far we have, okay, the square root of 2x minus 1, that can be replaced with the square root of u. So the denominator looks a little better. Dx, we could say, is du over 2. Okay, but we still have this pesky x up there. And remember, we can't have x's and u's in the same integrand. We have to have all x's or all u's. But we're trying to get away from x's because we're trying to simplify this using U-substitution. So let's forget about the x. And let's see what x might equal if we rearrange the original substitution. So let's see. If we rearrange that, solve it for x, we could say that u plus 1 over 2 equals x. Okay, so u plus 1 over 2 equals x. Now let's see here. So we can make that substitution. Now let's go ahead and just break that apart. That'll be one less step inside of our integration of our integral. So we'll have u over 2 plus 1/2 equals x. Okay, so u over 2 plus 1/2 equals x. Okay, now let's see what's going on here. So we have our substitution for x. That got rid of the x on the top. We have dx's substituted with du over 2. We have the square root of 2x minus 1 is replaced by the square root of u. So we have all u's. Now here's the thing. Well, here is what we need to do. We need to change the limits of integration. I can't put a 1 and a 5 there because a 1 and a 5, it refers to a function of x. But now we have a function of u, and I'll explain geometrically what's going on here. I'll show you a graph in just a few minutes, but it's really simple. It's just a really simple thing you have to remember to do, and that is use your original substitution to change the limits of integration. That is, if x equals 1, what does u equal? Well, okay, let's see. 2 times 1 minus 1. Actually, it's still 1 in this case. But it's not 1 because it was originally 1. It's 1 because we plugged into our substitution, and 2 times 1 minus 1 means u is 1. Now what about 5? Let's do the same thing. If x equals 5, then u equals 2 times 5, which is 10, minus 1 is 9. So now we're integrating from 1 to 9 instead of 1 to 5. And so let's see what happens. Now this is pretty weird looking right now. Let's do some algebra real fast. We need to rearrange this to make it look a lot better. First of all, let's factor out that 2 as a 1/2. That'll get rid of that 2 on the denominator. Now let's see here. I think we should, okay, we have this divided by this. We could probably rewrite this as 1 over the square root of u times, so I'm flipping the denominator and multiplying by the numerator, u over 2 plus 1/2. That looks a lot better. And then I, of course, have a du out there. So I flipped the denominator and multiplied. And now we can use some of those same techniques we have in previous exercises. So we have a 1/2, can't forget about that. 1 to 9 are the limits of integration. Now let's see here. Can we actually go ahead and do this? Let's call that a u to the 1/2 power, so we don't have to waste another step here. So that was the square root of u, which is u to the 1/2 power. Okay, so now if we distribute, we'll have, okay, let's see, we'll have u over 2 u to the 1/2 power plus 1 over 2 times u to the 1/2 power du. Okay, almost there, almost ready to antidifferentiate. So we have a 1/2 out front. We're taking the definite integral from 1 to 9. Now, what does this term simplify to? This is a u to the first power, understood first power, over 2u to the 1/2 power. So 1 minus 1/2, that results in 1 over 2, 1/2 minus 1, u to the 1/2 power, plus 1/2 times u to the negative 1/2 power if we bring that exponent up into the numerator. And now we're to the point where we can finally antidifferentiate. But remember, now we're doing the fundamental theorem of calculus because this is a definite integral. So we're not done after we find the antiderivative capital F of x. So we have a 1/2 out front. Now let's see, the antiderivative. So we have a 1/2. In fact, let's go ahead. Since we have a 1/2 here and a 1/2 here, we can factor out a 1/2 across the entire integrand. Oh, I forgot parenthesis there. Over the entire integrand. And if we factor out another 1/2, we'll have 1/2 times 1/2, which is 1/4. That'll make the antiderivatives a little less complicated. Now, what's the antiderivative of u to the 1/2? Well, it's u to the 3/2. Now, divided by 3/2 plus, okay, remember we factored out the 1/2, so we have u to the negative 1/2 plus 1 power, so it's u to the 1/2 power now. So it's negative 1/2 plus 1 is positive 1/2. Divided by 1/2. Now, since this is definite integration, we don't have to worry about that plus c. Now, you could if you wanted to. It wouldn't hurt anything. The c would go away in just a few minutes, but we won't worry about it. And we put this notation 1 to 9 to indicate that we're about to apply the fundamental theorem of calculus. Now, let's do one last step here before we actually apply. If you divide by 3/2, that's like multiplying by 2/3. So we can say just 2/3 right there. And if we're dividing by 1/2, that's like multiplying by 2. So we can actually just put a 2 right there. And now we can apply the fundamental theorem of calculus. Recall, we haven't done that since last lesson, but recall what it says. It says this is capital F, which is our antiderivative. Capital F always represents the antiderivative. We evaluate capital F, evaluate at our upper endpoint, and then subtract capital F at our lower endpoint. So we need to use lots of parentheses. In fact, I'll use a bracket around the entire process and parentheses around the individual terms. So or the individual capital F evaluations. So that's going to be 2/3. Excuse me. 2/3 times 9 to the 3/2 power plus 2 times 9 to the 1/2 power. That is capital F evaluated at 9 minus capital F evaluated at 1. So 2/3 times 1 to the 3/2 power plus 2 times 1 to the 1/2 power. So that is capital F evaluated at 1. So use lots of parentheses and be careful. So let's see what we have here. We have a 1/4 out front that we can't forget about. Now let's see what's left over here. Now 9 cubed is 9 times 9 times 9 is 729. 9 to the 3/2 power means you take 9, raise it to the 3rd power, and then take the square root. I think it's 27. Yes, 27. So we have 27 times 2/3. So 27 times 2 is 54. Divided by 3 is 18. So that worked out kind of nice. So that's 18 plus, okay, 9 to the 1/2 power. That's the square root of 9. So 3 times 2 is 6. So 18 plus 6 minus, well, 1 raised to the 3/2 power is 1. So that's just 2/3. Plus, okay, 1, the square root of 1 is just 1. So plus 2. So getting there, we have 1/4. Now let's see, we have 18 plus 6. 18 plus 6 is 24. Okay, then we have minus, distributing our negative sign, minus 2/3, minus 2, and we get 64 over 3. But of course, times 1/4, and we're almost out of room here. We get 64 over 12, which simplifies to 16/3, way down here at the bottom. 16/3. Okay? Now, I have my fingers crossed, hoping I didn't make any little mistake anywhere. I don't really rehearse these. I just kind of pick problems that seem interesting and hope they all work out. Now, I did make sure to program a picture for this. Okay, so I wanted to show you graphically what is going on. So what I'm going to do now is pull up that graphical representation of what U-substitution did for us and show what geometrically, graphically is going on. So let's see, the area, now I don't recall if this function's non-negative or not, but the net area is 16/3. Recall the original function was way back up here, x divided by the square root of 2x minus 1. Okay, so let's see. I'm going to pull up the graphical software and see what we have going on here. Okay, so here is the original function we were trying to integrate. Notice I have looked from 1 to 5, and our function is non-negative over 1 to 5. So the interpretation of the definite integral from 1 to 5 of f of x is area. So the area under the curve between the x equals 1 and x equals 5, those two vertical lines, and above the x-axis is this shaded area, which we found was 16/3. Okay? Now what we did with U-substitution is we translated that into a new function. Okay? That new function was u to the 1/2 plus u to the negative 1/2, and it was all times a 1/4 on the outside, and the new limits of integration were from 1 to 9. Okay, so here is the graph of the new function. So this is what we were trying to find originally, but when we transferred to u's, this is the new function. And what U-substitution, the beauty of U-substitution, is that those two shaded areas have the exact same value. The area of the red shaded area, the area is exactly the same as the blue shaded area. But whereas the blue function was hard to integrate, we transformed it to the red function, which we could integrate. It took us a little while, but it wasn't impossible. And they both have the exact same area. That is, the integral from 1 to 5 of f of x was the exact same as the integral from 1 to 9 of the function in terms of u instead. So that's what's crazy cool about integration by substitution, is that we have these two different functions, and in a lot of cases over different intervals of integration with different limits of integration, but the integrals are exactly equal. U-substitution says, hey, let's find a new function that's for all purposes, for all practical purposes, equivalent to our old function. We'll just have to change the endpoints, and we'll get the exact same value for the integral. That's what's cool about U-substitution. So I'll show you a couple of these graphs. The next one's even more cool than this one, but we're going to graphically find a different region with a different function that has the exact same integral as the original function. And that's what's cool about U-substitution. So let's look at another example. This next example is a little more tough, but we can work through it. So let's see here. It looks actually very similar to it looks very similar to one we've done before, but let's see. It's actually going to be a little more tricky. So let's see here. Let's look at the definite integral from 0 to 1 of x squared times the square root of 1 minus x dx. Now, we've looked at an example prior that was a radical, where the radicand was, I think it was 2x minus 1, and it was multiplied by x. But this time it's pretty different because there's an x squared out here. Because let's see what happens when we, let's just say we try to let u equal the inside function. If we try to let u equal 1 minus x, well then du equals negative dx. And so we start replacing things, and we quickly run into a dead end. We get the square root of u, okay, dx, then we get, so du would be, dx would be negative du, so negative du, but then we have an x squared over here, okay? So that's a little strange. So here's what I think we should maybe do instead. Pick a different substitution. What if we let u not equal the inside function at this point, but what if we let u equal the square root, 1 minus x? Now, let's do some rearranging before we take the differential. What if we said, okay, u squared is 1 minus x, right? Okay, we could square both sides of that equation. What if we then said, let's see, du would equal 2u du equals, let's see, negative dx. So what does du equal? Du equals, oh no, what does dx equal? Sorry, I'm trying to solve this for dx. Negative dx. Negative 2u du equals dx. Okay, so that's good for us. Now I have an x squared over here, so what does x squared equal? So I know what dx equals, I'm going to need that part. I know what u equals, it's this middle radical, but what about x squared? Well, I could say that that x, if I use this, I could say that x, now let's see, if we try to solve that for x, we would get x equals 1 minus u squared. But what if I square both sides? I would get x squared equals 1 minus u squared. Okay, so now I think I actually have all of the things that I need to make a proper substitution with only u's. Now I'm going to, okay, this is my green. I'm gonna back up a little bit to give this a little more room. This is the antiderivative. Excuse me, this is not antiderivative, this is definite integral. Now, I'm gonna have to change my endpoints in just a moment. Now, if, let's see, x squared we said was 1 minus u squared squared. So 1 minus u squared squared. Now, the square root of 1 minus x, that was just u. And dx was negative 2u du. And notice, now I have all u's. There's no x's anywhere, so that's exactly what I wanted. It took a couple substitutions. But notice I need to translate my endpoints. Now let's see. I need to go back to my original substitution and say if I know that x is 0, then what is u? Okay. If x is 0, then 1 minus 0 is 1. Take the square root of 1, you get 1. So the new lower limit of integration is 1. Now my original upper limit of integration was 1, but if x equals 1, 1 minus 1 equals 0, square root of 0 is 0. So now look what happened. This actually looks kind of funny because now we're going from the lower limit of integration is a larger number than the upper limit of integration. That looks weird, but just roll with it. If it really makes you feel better, you could use the property of definite integrals that says if you swap the limits of integration, you can just place a negative sign out front if that makes you feel better. But I would just say roll with it. Just leave it. It doesn't make a difference. Just proceed as usual and apply the fundamental theorem of calculus. There's nothing wrong with the upper limit being a smaller number than the lower limit. Just roll with it. So let's see. So from 1 to 0. Now we have some rearranging to do here. Let's see. We can factor out a negative 2 for sure. Factor out a constant. Now we have what's left over, 1 minus u squared squared, and then we have u times u, that's times u squared du. Okay, let's do this. Let's just multiply this 1 minus u squared, so it was squared. Let's FOIL it. So just off to the side real fast, let's see. We have, let's see, 1 minus u squared times 1 minus u squared times u squared. So I think if we FOIL this, then distribute, we can rewrite the integrand pretty nicely. I would say let's try to find another substitution, because you can use substitution twice in the same problem, but I don't think that's going to work out for us, because if I let's let v equal 1 minus u squared, then dv would equal not something that would help me out. So I think this is to be the best route at this point. So let's FOIL. So we have 1 times, okay, we have negative u squared, and then another negative u squared, so that's minus 2u squared. And then we have negative u squared times negative u squared, that's plus u to the 4th power. Okay, distribute, and that means we have a u squared, we have a minus 2 to the u to the 4th power. I'm just distributing, and then we have a u to the 6th power. Okay, so I've just multiplied the integrand so I can rewrite it, and we have negative 2 times 1 to 0, the definite integral. Now I have u squared minus 2u to the 4th plus u to the 6th all times du. All right. Now, we know that we can take the antiderivative of each of these items individually before we apply the fundamental theorem of calculus. So let's see here. We have negative 2 out front, of course. Now let's find the antiderivative. The antiderivative of u squared, that's easy. U cubed over 3 minus, okay, let's see, the antiderivative of u to the 4th is u to the 5th over 5, but we have a 2 out front, so that's negative 2 u to the 5th over 5. Antiderivative of u to the 6th, that's easy. U to the 7 over 7, we actually already have done that today. And now we have found the antiderivatives. Now we simply need to apply the fundamental theorem of calculus. Now don't think that we need to, for some reason, do capital F at 1 minus capital F at 0. The fundamental theorem of calculus says do capital F at your upper endpoint minus capital F at your lower endpoint. So they're switched, so it looks funny, but just follow the rules and you'll be fine. So let's see here. Capital F at 0 is what, do you think? Do I even need to write it out? Capital F at 0 is 0 cubed over 3 minus 2 times u, 0 to the 5th over 5, 0, 0, 0 to the 7th over 7. It's all 0. So capital F at 0 is 0. Minus, now do make sure not to lose your parentheses, capital F at 1, 1 cubed over 3 is that's just 1/3. 2 times u to the 5th over 5, that's just 2 over 5, so minus 2 over 5. Capital F at 1, you have u to the 7th over 7, so that's just 1 over 7, so plus 1 over 7. So what do we have here? Negative 2 times what? Negative 2, okay, notice we have a negative sign here, so it's going to be, let's simplify inside the parentheses, then negate the answer. So let's see, 1/3. 1/3 minus 2/5. I'm being lazy and using my calculator right now to be a little on the speedy side. 1/3 minus 2/5 plus 1 divided by 7. Yeah. And so for inside those parentheses, I get 8 over 105, but it's negative 8 over 105. Okay, so now we have negative 2 times negative 8 over 105. That gives us 16 over 105. Cool. 16 over 105. Now let's take a look at what's going on. I'll pull up another graphical interpretation. Let's see. So our original function was this. The original function was x squared times the square root of 1 minus x. And we were looking at the original limits of integration ran from 0 to 1. So the function was non-negative over 0 to 1. And so the interpretation of the integral, the definite integral, was area. So this green shaded area is the original definite integral we were trying to take care of. We were trying to evaluate. But remember, we didn't have a good way to do that. Okay, maybe in the future in a different way, but for right now, we didn't have a way to do that. So U-substitution is when we translated that function into a new function in terms of U with new limits of integration. Now, the new function was essentially we had a negative 2 out front, so if we multiply that negative 2 back into the integral to get what the actual function is, it was negative 2x squared, or negative 2u squared, plus 4u to the 4th power minus 2u to the 6th power. And the graph of that function looks like so. Now, I hope it clicks with you right away why the limits of integration ended up being reversed for that integral in terms of u. Remember in the integral in terms of u, we were integrating from 1 to 0 backwards, essentially, instead of from 0 to 1. And what does that do algebraically? It means you have a negative sign in front of your answer. Now, why is that important? Because this entire new function, u squared, negative 2u squared plus 4u to the 4th minus 2u to the 6th, it lies completely below the x-axis. That means the integral, if you integrate from 0 to 1, will give you a negative answer because it's entirely under the x-axis. But if you integrate backwards, which is exactly what our substitution led to, if you integrate backwards, then you add a negative sign in front of the integral, and you negate the negative answer, and you get a positive number. Thus, we integrated this orange area backwards and got the exact same number as we did for the integral for the original function in terms of x. So what U-substitution tells us is that this green area has the exact same area as the area of this orange area. The one weird and kind of cool thing is that the orange area is below the x-axis. So it means that the integral will be negative. It'll be the opposite of the green, except that when we closely followed the properties of U-substitution, then what happened is we ended up integrating backwards, which meant that we got the exact same positive number as we should have gotten for this area of the green function. So that's what's really cool. You're integrating completely different regions. In this case, the same endpoints, just in reverse, but you get the exact same answer for the integral. That's what's super cool about U-substitution. I think it's awesome. I hope you guys think it's really cool as well. So, different integrals, sometimes different limits of integration. In the next example, I'll show you how that would be completely different limits of integration, but you get the same value for the integral. Okay? So, really cool stuff. Now, I'll look at one last example, and then I'll just talk about a few different properties of even and odd functions, how those relate to integrals. All right, so the last example I want to look at for U-substitution before we move on to just one last little bitty topic is this example. We want to look at the definite integral from 0. So this is a trig. We haven't done a trig definite integration yet. 0 to pi over 2. 0 to pi over 2 of cosine x, sine x over the square root of cosine squared x plus 36 dx. I saw this in a different textbook the other day, and I thought it was a really cool example. Okay, so I was just reading, trying to prepare for some lessons, and saw this was a homework problem. I said, "Oh, that looks kind of tough," and tried to look at it. It took me a few minutes, but I figured it out. Okay, so it's in the substitution section. So that's why clearly, if it's in the substitution section, you're probably gonna need to substitute. So I had to play around with the substitutions, though. What I found out was, I didn't taking the cosine squared plus 36, like the inside function of the denominator, didn't get me anywhere. So I'm going to skip that roadblock. You'll get into a roadblock if you try to do that. But what I noticed is if you let just cosine be u, cosine x be u. I should say let u be cosine x. I don't know why I did that. Let u equal cosine x. Then du equals what? Well, it's negative sine x dx. Just remember the derivative. The derivative of cosine is negative sine. Okay. So, but what can we do at that point? With our substitutions. So let's not write the limits of integration just yet. But let's see what we can do. Well, in the denominator, we get square root of cosine squared. So that's u squared. U squared plus 36. Okay, on the top we get u, but okay, negative sine x dx is du. So we could say what? Well, okay, sine x dx is du. If we did this, if we multiply both sides of this equation by a negative, we would get that negative du equals sine x dx. So we could say, make that substitution now. So u times, actually it's negative, so times negative du. Since sine x dx is negative du. Now let's think about, okay, all I have is u's. That's really good. That wasn't too bad. So I need to change my limits of integration. Okay? If my original limits of integration were going from 0 to pi over 2, let's plug that into the original substitution. So if x is 0, what's u? Well, cosine of 0 is 1, so my new lower limit of integration is 1. Let's see, what's cosine of pi over 2? So if x is pi over 2, cosine is what? Well, that's 0. So the same thing that we just saw happened, okay? We're going from 1 to 0. Now, let's do a little rearranging up here. So we're going from, in fact, let's use that property of definite integrals, which says you can flip the limits of integration, but all you have to do is add a negative sign out front. So now we have 0 to 1 instead of 1 to 0, but I added a negative sign out front. But let's see. We have u squared plus 36. Now, what do I have on the top? Okay, I have a u. I have a du. But actually, in fact, I'll just put that on top still, u du. But I have a negative sign. But let's say I factor that negative sign out. Well, now I have two negative signs out front. And so I have negative times negative, I have a positive. And so my result is the definite integral from 0 to 1 of u du over u squared plus 36. Now I came to this spot and I thought to myself, almost looks like inverse trig, but I have a pesky u up here. And we don't do inverse trig in this class. That's where kind of you start off in Calc 2. So I'm thinking, why would they give us an inverse trig, or is that, and then it hit me, oh, it's not inverse trig. Okay, you'll learn about that pretty soon here in Calc 2, not in my class. But if you go to, not this semester, but if you go to Calc 2, you're going to learn all about trig substitution. And this almost looks like it might be, but not exactly. And so what we have to do here is then pick another substitution. So this is a crazy two substitution problem, double substitution. What if we let, now I have to pick a new variable. V is like the customary variable. So I'll let V equal, I think it was U squared plus 36 is maybe what I used. So instead of U's, I use V's. And now what is dV, the differential of V? I need to make really sure I differentiate the V. It's a sharp cusp and U is kind of curvy. So that is 2U du. So I take the differential of V with respect to U is 2U du. Okay. Now let's see what we can do with the substitution at this point. So we have the definite integral. Now I let U squared plus 36 equal V. So on the denominator I'm left with the square root of V. Now what about the numerator? Okay, I need I have a U du. So if I wanted to put in a U du, I would need to divide both sides, or I could just, this is probably the easier way to do it. Don't even worry about dividing anything. Say if I needed 2 du there, I would have to multiply by 1/2 out front. Okay, I multiplied by a 2 over 2. I took in the top 2, and now I have 2 du, 2u du, sorry, and that equals dv, and then I have a 1/2 out front. But notice, I have a new function in terms of v. My endpoints of integration, my limits of integration, the 0 and the 1 only work for u's. So I have to change my limits of integration yet again. So if u was 0, what does v equal? 0 squared plus 36 is 36. If u equals 1, what is v? 1 squared plus 36 is 37. Okay? And now look at this nice integral we're left with. The definite integral from 36 to 37. What is this? It's v to the negative 1/2 dv. That's a super easy integral to take care of now, because we know, okay, we have this 1/2 out front. We know the antiderivative of v to the negative 1/2 is, okay, increase the power by 1, so that's positive 1/2. Divide by that new power, which is 1/2, and we evaluate at 36, from 36 to 37. So we have a 1/2 out front. This simplifies to 2 times the square root of v, and we're going from 36 to 37. And so we have 1/2. Capital F is 2 square roots of v. So that is 2 square roots of 37 minus capital F of a, which is 2 square roots of 36. And what do you know here? 1/2 times this, 1/2 times that. Using the distributive property, we get the square root of 37 minus the square root of 36, which I'm not going to waste another line here. We all know the square root of 36 is 6. So notice, after all that, two substitutions, starting with a weird trigonometric integrand, we get rid of the trig pretty soon, and our final answer is the square root of 37 minus 6. So here's what I contend. I contend that if you graph, so if you're going to graph these, you have to bring the constants back in. So if you graph v to the negative 1/2 over 2, and you look from 36 to 37, and if you graph, let's see what we have here, this right here, so bring in the negative, so it's negative u over the square root of u squared plus 36. Oh, no, we made a double negative, so that was a positive, so we can erase that. So if we look at this function from 0 to 1, and then if we look at this function from 0 to pi over 2, the integrals, the definite integrals of each of those three functions will yield the exact same number. I thought that was super cool. Let's look at a graphical. Let's look at this graphically, and let's see what we have here. There's the original function. It is non-negative, so the integral interpretation is area. So the integral from 0 to pi over 2, a little past 1.5, is this shaded area above the x-axis, this red shaded area, okay? Which we found to be was the square root of 37 minus 6. It's a little bitty bit of area, because the square root of 37 is just barely bigger than the square root of 36. So this little bit of shaded area. Then we found out, okay, that's a tough, that cosine times sine divided by the square root of cosine squared plus 36, that was tough to, to leave how it is and anti-differentiate. So since we didn't have a good way to anti-differentiate it directly, we translate it in terms of u and say, hey, here's a new function. It's u divided by the square root of u squared plus 36. And this is what it looks like. And we're going to look at this function we said from 0 to 1. Instead of the original function from 0 to pi over 2, we're going to look at this one from 0 to 1. But it's going to have the exact same integral as the red function. So this blue shaded area is exactly the same as this red shaded area. But then we said, all right, well, that's still kind of hard to anti-differentiate it directly. So let's write a new function. Now this new function we found out was 1/2 times, it was 1 over 2 square roots of x. Okay, but we're going to integrate that from 36 to 37, which is way over here to the right. This little bit of area over here. And so what this whole idea of U-substitution is that this green integral area, and since all these functions are non-negative, the interpretation for all of these is area. So the area between 36 and 37, x equals 36, x equals 37, but below this function 1 over 2 squares of x, that shaded area is the exact equal to this red shaded area, which is exactly equal to this blue shaded area. Those three regions are exactly equal to each other. That's what's really cool about substitution. So you're rewriting a new function, perhaps over a different interval. Notice the first one was over 0 to pi over 2. The second one was over 0 to 1. And the third one was way over here from 36 to 37. But they all have the exact same value for the integral. Really cool stuff, U-substitution. Again, this takes substantial practice. You develop an intuition over time by practice. But if you don't practice, then it's really going to be tough to tough to see a lot of these steps and figure them out. You know, it's going to be tough at first, but as long as you put the time into practice, it won't be so bad. Okay? Now, last thing we need to talk about are even and odd functions. So the last theorem down here is referring to even and odd functions. Theorem 5.16. Oh, by the way, I kind of skipped the official Theorem 5.15. I just showed it to you in practice. The only thing is it's showing you how to get the new limits of integration, which is exactly what I showed you how to do. So it's saying, you know, we called it U, here they're calling it G. Remember, g of x is what we're calling our function, our inside function U. Let's see what Theorem 5.16 says. This is talking about even and odd functions. Now, this theorem only applies to when you're integrating from a to negative a. Okay, or I said it backwards. From negative a to positive a. Okay? So you have a function, and you're looking at, say, the definite integral from negative 5 to positive 5. Or from negative pi over 2 to positive pi over 2. Or from negative 10 to positive 10. When you're looking from, you know, from the exact same distance from the origin in both directions. So this theorem only applies to that situation. So it says if you have, let's start with the second item. It says if you have an odd function, here's what's awesome, is that if you are integrating from negative a to positive a, and f of x is an odd function, the answer is always 0. So be on the lookout for situations like this, because the answer is always going to be 0. If you know that you're integrating from negative a to positive a, and you know for sure that f of x is an odd function. Now, I'll show you why this is true in just a sec, but let's talk about item 1 now. If you have an even function, and you're integrating from negative a to positive a, what you can do, if it helps you out at all, which usually will make the arithmetic a little simpler, is you can notice, all right, if it's even, then that means it's symmetric with respect to the y-axis, which means you'll have the exact same amount of value for the integral from on the left side of the origin as the right side of the origin. And so you can instead integrate from 0 to a and multiply that answer by 2. Now let's explore why both of these things make sense. So we have, let's just look at, say, let's look at sine and cosine. Those are two basic ones. So if you look at sine, anybody remember what sine is, if it's even, odd, or neither, or something like that? Well, I think if you remember what the definition of an odd function is, sine fits that. Because an odd function is symmetric with respect to the origin. Now, what does it mean to be symmetric with respect to the origin? Well, I mean, if graphically it means if, so odd, let's say odd, means if x comma y is on the graph, then negative x comma negative y is also on the graph. You know, that's if you're thinking about symmetry. So what that says is if this point is on the graph, then if you negate that x value and that y value, this point over here has to also be on the graph. That's what an odd function means kind of graphically. Now, if you want to check this, if you want to check it algebraically, here's the test. Show f of negative x is equal to negative f of x. That's what you have to do. Now, sine, we know that's true from trig. We know that's true. So here's what that second part of the theorem says. That second part of the theorem says, hey, if you integrate, let's say pi over 2 to negative pi over 2. So we have, this is sine x, and we have negative pi over 2 over here. Oh, I put that on the curve, and pi over 2 right there. If we integrate, we're finding, since this function is not non-negative, the interpretation is net area. So it's this region and this region, but the region above the x-axis counts in a positive manner, and the region below the x-axis counts in a negative manner, and they're the exact same size. So you have negative plus a positive, exact same number, except they're opposites. Well, I should say they're just opposite numbers. They're not exactly the same. So they add to 0. So we can say for sure that the definite integral from negative pi over 2 to pi over 2 of sine x dx equals 0 because sine is an odd function. Okay. Now let's show. Let's show using the fundamental theorem of calculus. Okay. How would you solve this using the fundamental theorem of calculus? Well, we would say, what's the antiderivative of sine x? Okay. What do you take the derivative of to get sine? Okay, it's negative cosine x. This is, that throws people off because with the relationship between sine and cosine with derivatives is kind of the opposite with integrals, antiderivatives, because of the negative sign. So we have negative pi over 2 to pi over 2. Now, why is that true? Take the derivative of negative cosine. The derivative of negative cosine is negative sine, also known as positive sine. So there we are. All right, so let's see. The fundamental theorem of calculus says evaluate. Okay, we have capital F, which is negative cosine x, at pi over 2. So negative cosine pi over 2 minus capital F evaluated at A. Okay, so that is minus negative cosine at negative pi over 2. Okay, what's cosine of pi over 2? Well, cosine of pi over 2 is 0. So that's 0 plus what's cosine of negative pi over 2? 0 equals 0. So there, let's say you were trying to solve this definite integral. Well, hopefully you can recognize, sine is odd, the answer has to be 0, and that's your justification. Just say you're on a test, just write down sine x is an odd function, therefore the integral from negative pi over 2 to pi over 2 is 0. And you can save yourself, especially if the integrand is a harder one to handle. Let's say it was several terms, and you could show that it was still an odd function, then that would be much easier than actually finding the antiderivative and using the fundamental theorem of calculus. So you just save your time. It's a time saver. Okay. Plus, for every step here, there's a possibility of making an error. So it saves you time, and it saves you from making potentially errors. Okay. So that works with any odd function. For instance, if you look at, let's just look. I won't work it out, but if you have, say, the polynomial x cubed. So x cubed looks like this. Okay, it's symmetric with respect to the origin. It's an odd function. So let's say we were integrating from negative 4 to positive 4. Well, notice what happens again. You have the same amount of area above and below the x-axis. They're going to be the exact same number, but since this area, this region over here, is below the x-axis, it's going to be counted in a negative manner, and the region above the x-axis is going to be counted in a positive manner. So the net area will be a number plus its opposite equals 0. In fact, I'm not in a huge rush here. Maybe you're in a rush, but you can always pause and come back later. If you look at the, this would be the integral from negative 4 to 4 of x cubed dx. Okay, the antiderivative is x to the 4th over 4, and we're going from negative 4 to positive 4. So that is negative 4 to the 4th power. Okay, negative 4 to the 4th power is going to be positive. Now what's 4 to the 4th? It's 256. So you get 256 over 4 minus, okay, we have negative 4 to the 4th power again is positive 256 over 4 equals 0. And that's always going to happen when you have an odd function and you're integrating from negative a to positive a. So negative 4 to positive 4. Always going to happen. Now, what about the other situation? You know, the other part of the situation is what if you have an even function? Now, if you have an even function, it's not quite as helpful, but it's certainly helpful in some regard. Now, what's a common even function? Well, x squared, that's a common even function. So let's say we have f of x equals x squared. Now remember, oh, I can't draw a parabola to save my life. I suppose that will do the job. Remember, even. Even function. Graphically, if x comma y is on the graph, then negative x comma positive y is on the graph. Algebraically, you want to show that f of negative x equals f of x. That's how you show algebraically that a function is even. For instance, points, if this point is on the graph, then this point has to also be on the graph. So if you're trying to show, say, f of x equals x squared is even, evaluate f of negative x equals negative x squared. But we know that if we take a negative number and square it, you always get a positive result. Well, at least non-negative. If x is 0, you get 0. So we know that's true. Well, guess what? F of negative x equals f of x. Thus, the function is even. Now, here's what the theorem said. The theorem said that if you have this situation and you're integrating, let's say, from negative 2 to positive 2, then your answer is the exact same thing as double either side. Specifically, if you want to go from 0 to 2, then that will work. So we could do this. We could say the definite integral from negative 2 to positive 2 of x squared dx is equal to 2 times the definite integral from 0 to 2 of x squared dx. Now, where might this be super useful? This would be super useful like if you're doing a Riemann sum. Why would it be useful? Because let's envision you're trying to do this as a Riemann sum. I'm not going to work it out since we did that on a different day, different video. But if we were going to evaluate this Riemann sum, we would say, all right, it's the definite integral from negative 2 to positive 2 equals of x squared dx equals the limit as n goes to infinity of the sum I equals 1 to n of the f of c sub i's times delta x. Now we'll use rectangles of equal width, so we won't index those. And we'll say this equals the limit as n goes to infinity of the sum I equals 1 to n. Now, what are our endpoints? Well, recall that endpoints for right-hand endpoints, the c sub I are the a, which is negative 2 in this case, plus delta x. Now delta x is the width of the interval divided by n. So that's 2, the width of the interval is 4. So 4 over n times I. So delta x equals 4 over n. So we're going here, we have, okay, negative 2 plus 4 over n times I. That's f of c sub I times delta x is 4 over n. Now, is that, terrible to do? Well, what is f of c sub I? Well, it's a limit. We have limit as n goes to infinity, the sum I equals 1 to n of that squared. Now, is that impossible to do? No. But look what would be a lot easier. We could go instead, at this point, we could say, here, let's do this in a different color. We could say that this would be equal to the limit as n goes to infinity, the sum I equals 1 to n. Okay, so what if we notice this is an even function? We could say, okay, forget about c sub I equaling this. Let's integrate from 0 to 2. In fact, let me go actually put that here. We could say this is instead equal to the 2 times the integral from 0 to 2 of x squared dx. Which now, look at this sum. Limit as n goes to infinity. The sum I equals 1 to n, but look at delta x and the c sub I now change. Because remember, delta x is the width of the interval divided by n. So what's the width of the interval now? It's 0 to 2. So it's 2 over n. What's c sub I? Well, c sub I is the leftmost endpoint, which is 0, plus 2 over n times I, delta xi. So now we have f of 2n times I times 2 over n, which is the limit as n goes, I forgot that 2. I lost the 2. 2 right there. 2 right there. 2 times the limit as n goes to infinity. The sum I equals 1 to n of 2n times I squared times 2 over n. Now, I'm not going to complete these, but notice the one on the left is a lot easier. I do this all the time whenever I see a Riemann sum from negative a to positive a. Because a Riemann sum where the a is 0 is much easier to work with if you have a quadratic or a cubic or something like that. Much easier to work with than if your leftmost limit of integration or the leftmost endpoint, the lower limit of integration, is a different number. So negative 2, we're going to have to FOIL this because we have to square it. Here, we're squaring a single term, and so the algebra is a lot easier. And all we have to do is get to this limit, multiply the answer by 2, which will be the exact same answer we get over here. Okay, so that's this is really helpful. I wouldn't say it's much as helpful as the odd function relationship, but it is helpful if you're doing Riemann sums, or the fundamental theorem of calculus just ends up being easier if the lower limit of integration is 0. I mean, just on a very basic level. Like, let's look at this example. We had let's not do the Riemann sum. Let's just do the fundamental theorem of calculus. Let's say we just do instead the first way. Okay, that is, okay, let's do the antiderivative. That's x cubed over 3. And that is from negative 2 to positive 2. All right, well, that's not so bad. I mean, the fundamental theorem of calculus says, all right, negative 2 cubed over 3. Oh, I did that backwards. It says 2 cubed over 3 minus negative 2 cubed over 3, which equals 8 over 3 minus negative 8 over 3, which is 16 over 3. Now, is that hard? No, but I mean, you have a negative sign here to worry about, so you double negative and make it positive. But what about if instead you said, all right, let's do it this way? Okay, still the same exact antiderivative, except we're going to say 2 times, okay, antiderivative is x cubed over 3. And we are going to evaluate that from 0 to 2 instead of from negative 2 to 2. We're just going to multiply our answer by 2. And what do we get? Well, it's 2. X cubed is, let's see, that is 8 over 3 minus 0. So notice, if you have a 0 as your lower limit of integration, the arithmetic when doing the fundamental theorem of calculus oftentimes is much more of a breeze. You don't have to worry about double negatives, and in this case, a negative number cubed and making sure that you know that's a negative number and all that kind of stuff. So the arithmetic, just on a very simple example here, ended up being easier. That's usually the case. So that's the nice thing about this relationship on an even function. Now again, I can't stress this enough. Both of these properties only work when you're evaluating from negative a to positive a. Like for instance, another classic example is cosine. Cosine is a even function. So if you look at, say, the integral from negative pi over 2 to pi over 2 of cosine x dx, we could say that is 2 times the integral from 0 to pi over 2 of cosine x dx. Let's show how you get the same thing, and I think we'll call it a day after this. Let's look on the left-hand side here. All right, so let's see. The antiderivative of cosine is sine x. Now we're evaluating from negative pi over 2 to pi over 2. So let's see here. That is sine of pi over 2 minus sine of negative pi over 2. Okay. So what's sine of pi over 2? That's 1. Minus, what's the sine of negative pi over 2? Negative 1. And so we get 1 plus 1 is 2. Let's see if it's any easier using the right hand rendition over here. Well, we could say the right hand side, that's 2 times the antiderivative, which is sine x evaluated at 0 to pi over 2. Well, so that's, what's the sine of pi over 2? That's 1. What's the sine of 0? That's 0. 2. Is it any easier? I guess maybe one step easier, sure. In these examples, what you want to do in general is just, be looking out for situations in your homework, quizzes, or tests. Be looking out for situations when you have the definite integral from negative a to positive a. Okay? And see, can I tell if the function's even or odd? Now remember, I gave you the criteria to algebraically show for a function to be odd. You're looking at, in both cases, you're evaluating f of negative x. And if once you simplify f of negative x, if you get the original function back, then you have an even function. But if you get the opposite of the original function back, then you have an odd function. So if you can show your functions even or odd, and if you look up I think I'll post out all of the rules of even and odd functions, like if you take the product of two odd functions, or the product of two even functions, or the sum of an even and odd function. We'll talk about those, or actually let's just look up those rules in an algebra book. Just Google, even and odd functions, because if you multiply an even and odd function, you get an odd function and stuff like that. So, just be able to recognize there's some shortcut ways to figure out if a function's even or odd if you look at some of the pieces. But in general, just be looking out for the situations where you're integrating, from negative a to positive a, and see if you can show is the function even or odd. If it's odd, then that's super nice. The answer is going to be 0. If it's even, just think to yourself, does it save me time if I integrate from 0 to a and then multiply the answer by 2? Does it save me time, potentially mistakes? Then sure, go ahead and do it. It's more just a simple time saver and really just cutting down some of the arithmetic. So I hope this has been helpful. We have covered a lot today as far as maybe not a lot of concepts, but a lot of examples. So lots of examples today that maybe took a little while to do as well. But let's just review, recap real fast, and then we'll get out of here for the day. We did U-substitution. U-substitution is what you have to do whenever you have composite functions, at least for the time being. Composite functions need U-substitution. You'll have some more nuanced techniques if you go into Calc 2, but right now, U-substitution. And by the way, substitution is going to be a major part of Calc 2 with trigonometry and inverse trig and all kinds of nice stuff is where you're going to start off in Calc 2. So let's see here. When we have composite functions, we're trying to reverse the chain rule to find an antiderivative. We also talked about how to use the U-substitution when you have a definite integral and how it's a really neat relationship about how you're finding a new integral with new limits of integration oftentimes, but the integrals are equal. That is, if the functions are non-negative, the areas are the same. Really cool stuff. We looked at a few graphs that showed that. And then lastly, we talked about if you have even and odd functions, if you have this special case right here, when you are integrating from negative a to a or vice versa, that is what you're looking for. And if you have that situation, try to recognize, do I have an even function or odd function? If so, apply one of these two theorems to make your life a little bit easier. So, hope this has been helpful. If you have any more questions, always feel free to ask. This always comes at the end of the semester, so it's always crunch time at this point. Just make really sure to give U-substitution the practice it deserves, because it doesn't come easily without practice. It's not something that's just you're going to be able to see it and figure out the first time. Practice is key. Asking questions if you need help is key. All right, so we'll talk soon. If you need any help, just let me know.